Okay, so we move on with our class on diffusion models, and our next topic is actually very practically, important. I think that's what made the diffusion models so affluent and so powerful, is that not only we can sample from a distribution, we can actually uh, tell the diffusion models what we want to generate. And so this is called guidance or control. So kind of almost unrelated, but it is still a related topic, because the idea is as follows. If we think about the diffusion as all of these steps of generating, taking a bunch of images, noising, adding noise, denoising them, and we can speed it up with consistency and whatever methods we mentioned. But how can we specify that we want to have this image of a girl with glasses in a specific style? Um, that becomes that text prompting or other methods like ControlNet actually make these tools practical for designers, for creators, for musicians. Um, so even if we learn this from a huge amount of images, we don't want to rely on the fact that we'll just randomly regenerate some kind of image. We want to do this, and we don't want to do this in a way that control that is learned by classes. Okay, we could in theory say, okay, we learn one diffusion models for, I don't know, or for human faces, or for girls with glasses. But I mean, that will defy the purpose of diffusion, to have this kind of a generative general purpose method of generating data. And yeah, of course, so these kind of examples, maybe just to make it more contextually related to music, but in terms of images. So if you want to have a musician performing with musical robots, you can have a lot of possibilities with adding style definitions and so on. So yeah, so we actually want to have this possibility of generating what we want without specifying every detail. So how is it done? And this brings us to this idea of, again, using the score-based formulation and adding this sort of a conditional step where now we want to learn a score function conditioned on some y. Okay, so y is our prompt, or the conditional variable. Now, if we use again Bayes' theorem, we can kind of break this down into this sum or sum difference of all these expressions. Now, what we can see is that we have here, we can kind of ignore the gradient of our condition, because this is gradient on x. This is why it doesn't depend on x. So there is no change in our conditioning, right? So we are left here with two things. One is our original unconditional score over all of the data we have. But then here we have something else, which is a conditioning on the prompt given the data. Okay, so we kind of use the Bayes thing to show this expression. And what actually is this thing? This thing could be considered as a classifier, right? So given the prompt, okay, now for all possible data points, we'll see what is the probability of this prompt matching the data. Okay, so we're going to invert this logic, and this is what a classifier does. Okay, classifier basically tells you, given a specific data, what is the probability of possible prompts. Okay, and so again, if you want an image of whatever that musician performing with musical robots, what is the probability that now another image will actually match this annotation? Okay, this is why it's called a classifier, because it's the probability of the target given your data. Now, we actually could use a classifier, and we can run this in parallel with the diffusion process. So every time we not only follow the score, we also shifted in the direction of the classifier. So we kind of, every time we denoise, instead of going just according to the general distribution of possible images or possible sounds and following this vector field, we bias this towards solutions that will classify correctly according to prompt that we also entered. This is the classifier guidance. Now, it does require us to design a classifier, which is a pretty annoying thing. So if you have networks that classify according to categories that you want, you can combine these two neural networks, and then you can generate unconditionally. And then every time, for every noise you run the classifier, you have to calculate this gradient and add this to the next denoising step. So it will kind of nudge your denoising towards what you wanted. Now there's another trick that became much more powerful and popular, which is called the classifier-free guidance, the CFG. So if you encounter this term, this is basically what it does. It can repeat the same logic, okay, of writing the classifier as a sum of, the original score function and this. So these two things cancel out, but instead of this, it introduces some kind of a weight factor. So it's not really a real gradient here. It's the original score and the difference between basically conditional generation, if we had trained it conditionally, and unconditional generation with some kind of a weight factor. Okay, so just kind of reworking out here the equation, we can rewrite this as a weighted sum between two types of generative processes. One is you have training data for a specific type of prompt that you want, okay? And another one is unconditional score. And if we now translate this to this denoising formulation, actually, instead of estimating only the epsilon theta, okay, what we do is we estimate two epsilon theta. One is the original one, and another one is a conditional one. So we basically create a new loss function that gives us the denoising. It's actually not a loss function. It's a new direction in the denoising. Okay, that's basically that makes this kind of a combination or trade-off between denoising the original data and denoising the conditional data. And using this basically allows us now to generate the prompts that we want. And so these kind of guidance nudging factors, it could be inserted into the different diffusion models in different ways. In stable diffusion, this is the denoising, the UNet that I mentioned before. You actually have this text injection, and it's done using cross attention. There's some other methods in DALL-E where you actually insert this, you learn a transformer from text embedding to image, okay? And this is not exactly the same guidance that we mentioned. Imogen kind of uses something a little bit similar to stable diffusion. And yeah, so that makes this kind of a process very useful. So let's look a little bit into the stable diffusion architecture. It uses a specific type of encoding of the condition of the text. And that'll be the topic of the next set of slides, but it uses so-called CLIP, which is contrastive language and image pre-training. Okay, it actually uses text and puts it in the specific representation vector or embedding that is joined with the image space. So I'll talk about this next. Once you do this, you actually have your denoising process through the UNet, okay? Diffusion happens here, and then it's processed together into a new image tensor that is eventually decoded into the image. Okay, so when we move from the diffusion in images to diffusion in audio, we had to recreate our own version instead of clap, and use our own decoder, okay, that takes this embedding space, and instead of decoding this into images, decodes this into audio. And so I'm just showing here a little bit more in detail. So how do you add context? Okay, if you need to learn now specific context embeddings, we kind of repeat the same structure for a limited set of contexts that we want to impose on our data. And they're actually add the decoding step, okay, as context embedding with you know, multiplication. There are some other operations you can add this also, um, with the feature maps at the decoding steps. So you actually decode this knowing what the context is. Okay. Yeah. So this is kind of another example where, you know, it actually uses the cross attention as the decoding process. Again, a lot of information. It really kind of just to point out to the main tools that are being implemented today for actually making the transformer process, diffusion process, controllable. Uh, kind of to give an idea of this guidance. So if you want to generate just conditionally on pandas without the guidance, you end up with very distorted images. If you do use guidance, you can see that you have a lot of variations, but it's very consistent with your original prompt. So as a summary, guidance is a method to make the generation be highly representative of your initial prompt or feature that you want. There are classifier and classifier free methods. Process using classifier free guidance is you predict the original noise, okay, without the text prompt, okay, and then also take some of, you know, fraction of the unconditional noise and this guidance scale, and also noise conditional uh, prompt, okay, the noise conditional noise value, okay. So you can make this little shift, okay, towards the noise condition, and that also shifts you towards your original design. Yeah, okay. So I think I'll kind of a little bit speed up because we have so many things to talk about, and this is all advanced and optional material at this point. So see you in the next video.